My name is Gun-hee Kim. I'm an associate professor at Seoul National University. Basically, our research lab focuses on the research about vision and language at the intersection of computer vision and NLP. However, as you know, these days, vision and languages are tackled by machine learning techniques. Therefore, we also do some machine learning research. So today, I'd like to represent some work about reinforcement learning. So if time permits, I will present 3 papers that are presented in recent NeurIPS and ICML and iClear. So let me begin with the first paper. This paper was published in NeurIPS 2021. Okay, so title of this paper is Time Discretization Invariant Safe Action Repetition for Pulse Gradient Methods. So here's the motivation of our research. So as you know, basically RL is formulated by MDP. So MDP means Markov decision process, and basically this is a discrete process. So it means that you have to formulate RL problem as a sequence of state, action, reward, and state. So basically MDP formulate the whole process with a sequence of state, action, reward, and so on. So however, most environment we'd like to apply RL is continuous time domain. So therefore, your first job is to discretize the time. So the idea is that you set delta, for example, 0.05 second, which means that you observe the state and select the action at every 0.05 second. However, this discretization is very critical to performance. So it means that here you can see some examples of RL environment. However, if you want to achieve the best performance in nth environment, you have to set delta to 0.05. And in another environment, you have to change delta again. And in another environment, you also need to select another delta. So it means that you have to test. If someone gives you a new environment, then you have to apply RL techniques many times by changing delta. So it's very tricky. So here, our goal is to make any pulse gradient algorithm to be invariant to delta. Invariant to delta means that no matter how you set delta, we'd like to make the pulse gradient performance equal. So invariant. So that's our goal. So for example, previously in Hopper environment, if you change delta, then performance probably degraded. But our goal is no matter how you can set delta, we want to make we want to get the same result from pulse gradient algorithms. So here's the reason why we need to care about delta invariant algorithm. So by doing that, we can skip the process for tuning delta, and we can get better performance with fine-grained delta. So I will give the more details about the second point. So basically, intuitively speaking, if you have a small delta, then the performance will increase, because reducing delta means that we give more fine-grained control to the agent. Therefore, ideally speaking, a low delta should lead to better or equal performance than high delta. However, in previous research, it is known that with a too small delta, Q-running and policy gradient performance degrades. So for the Q-runnings, these two previous work proved that with too small delta, you can observe performance degradation. And for the policy gradient, we derive one theorem to prove this. So this is the theorem in our paper, and basically this is a little bit long theorem, but the important thing is that this is the variance of your return. So here's left hand side, you can see the variance of the returns, and in the right hand side you can see delta in the denominator of the equation. So it means that if you goes to delta to 0, then right hand side is moved to infinity. It means that the variance of return explodes. So it means that if your environment is a little bit stochastic, then you will experience variance explosion of the policy gradient when delta goes to 0. So this is one reason why with a small delta does not guarantee a good performance. The second reason is this. So in many cases of RL problems, we need to address exploitation and exploration trade-off. However, if you have a small delta, then you will have less exploration. So it's very obvious. If you have small delta, then if you perform 100 action repetition, for example, then you can only explore only small region in the state space. However, if you have a high delta, then you can move further in the state space. Therefore, too small delta degrades the performance of exploration. So that's another reason why policy gradient method fail with too small delta. And another reason of why policy gradient fail with small delta is the third reason may be infinite decision steps. So if you have too small delta, then you have to make many decision steps to reach the goal. So by doing that, it would take so much time to reach the goal. So that's another reason. Therefore, there are some previous research to make your algorithm. Hold on a second. There's a question. Okay, yeah. So okay, so there has been some previous work to make your algorithm delta invariant. So one simple previous approach is that you change the policy. So basically the policy in RL is a function from state to action. So in many cases, the goal of RL is to learn good policy. So policy means we want to find out best action for a given state. So there are some previous work to make your algorithm delta invariant, and their basic approach is that they try to change the policy function, not only produce action as usual, but also number of action repetition. So it means that given the policy, these algorithms try to generate the best action at this point, and how many times you repeat these actions. By doing that, no matter how you set the delta, then we can simply increase W, right? Therefore, we can make our algorithm delta invariant. However, there are some limitations of prior approaches. The first approach is that they could fail in stochastic environment. Suppose that here's your agent is autonomous vehicle. So it tries to, so in a particular state S, your policy generate moving forward and 5 repetition, for example. So in this particular example, A is moving forward and W is going to be 5. However, in next time step, you suddenly observe pedestrian, then you have to change your action, right? However, this kind of approach already generate the number of repetition, so probably they may hit pedestrian. So that's one issue. So the idea is that they tries to keep the same action until its duration end. Here 5 times. So even when something unexpected happens. So this is one problem. And the second problem is that they are based on the locality of time. So it means that basically policy should be a function of S. However, given the state, they just repeat actions 5 time steps. So in this particular example, actions are repeated in time space, right? However, action should depend on state. Therefore, it's not a good idea. So our major contribution is we change the concept of repetition. So the idea is that previous research determined action duration based on time, right? However, our argument is that the action duration should be determined based on stage. So basic idea is that we change the policy so that it generate not only action but also the radius of the safe region. So in previous approach, they generate number of repetitions. However, here we define the radius of safe region. By doing that, if you can observe unexpected pedestrian, it means that your state will change a lot. By doing that, you can observe very severely changed state, then you can directly stop your action. So that's the basic idea. So here we use L1 norm to define the state differences. And if the state difference is larger than D, then we immediately stop our action repetition and we compute the best action at this state. However, in previous research, they already generate number of repetition. Therefore, they probably do the same action several times more. So we call our algorithm as safe action repetition, SAR. And so the advantages of SAR is that that approach is delta invariant like other approaches. So our threshold is defined in the state space, therefore it is completely agnostic to physical time variable. And the second advantage is that our approach is robust to stochasticity. So as I mentioned in pedestrian example, then we can immediately regenerate actions based on state change. So in our experiment, we apply our approach to 3 popular policy gradient methods. So our approach can be applicable to any policy gradient method, and we compare our SAR to figure C. So figure C is state-of-the-art delta invariant approach based on action duration. So here we perform 8 different Mozuko environments, and we change delta in 4 different ranges, and then we perform the experiment. So PPO means the original PPO algorithm, and figure C PPO means you apply action duration to PPO, and SR PPO is our proposed approach. So ideally, these 4 graphs should be the same, exactly same, no matter how to set delta, because ideally our approach should be delta invariant. However, in practice, the graphs are a little bit different. The idea is that y-axis represents accumulated rewards. There, as you can see, our approach achieves much better accumulated reward than other baseline methods. So for 8 different experiments, we show that our approach is better than figure C. And in the second experiment, we add some types of stochasticity. So it means that we randomly apply external forces to agent body, or so we apply 3 different types of stochasticity in the environment and observe the performance. As you can see, figure C shows much worse performance in these stochastic environments. So that's our main result. So here's the summary of the first paper. So our first contribution is that we prove that the variance of rewards of a policy gradient methods explode with as delta goes to 0. So that's one theoretic result. And then we apply delta invariant approach, and our idea is we repeat the action based on the state, not time. So that's the main difference. As a result, our approach is delta invariant and robust to stochasticity. So that's the end of the first paper. So this is a possible future directions, but you can just, it's not big things. So you can download the code of SAR, and this is the first author of this paper. So actually he was the undergraduate student, but he wrote 3 good RL papers, and he's now on PhD student at UC Berkeley. Okay, so now I'd like to move to the second paper. How many times? Okay, 2:40. My time is up to 3 p.m., right? Okay, so let's move to the second paper. So the paper title is Unsupervised Skill Discovery with Bottleneck Option Learning. So this is a basic RL setting. So here your goal is to define, in many cases we want to learn a policy. So policy means you want to find out. So this is the definition of a stochastic policy, which means that given a pair of state and action, you need to generate probability. So as a result, we want to find out which action is the best for a given state. So when we learn policy, our goal is to maximize the total accumulate reward. So often this is called return. So you are given environment. So environment is a kind of function that takes action as input and generate state transition and reward. So there's one big area called unsupervised skill discovery. So you can think of this as an unsupervised learning. Unsupervised learning of RL. So it means that in order to learn policy, in many cases we need to get external reward. So based on the external reward, we try to optimize the policy. However, in unsupervised skill discovery, we assume that we have no external reward. So here, our goal is to discover inherent skill in environment. So the idea is that given environment, you perform many different actions, and then you find out some action sequence that are useful for this environment with no external reward. So here's some examples of discovered skills. So it means that in half cheetah environment with no reward, the agent does a lot of repeated action and discover 4 meaningful sequence of actions or sequence of states as skills. So here, our goal is to discover diverse and distinguishable skills. Skills are trajectory of states. And here we assume that there's no reward. So given environment, you discover some meaningful skills in a completely unsupervised way, and those skills may be useful for the environment, no matter how you define the task is. So how we can discover this kind of these diverse skills? So the basic idea is that we use some kind of VA-like approach. So the idea is that we define latent space Z, and this is called the skill latent vector, and we assume that Z is sampled from some fixed prior. So the idea in this unsupervised skill discovery task, instead of learn normal policy, we try to learn skill conditioned policy. So for better understanding, you can think of a VAE. So in VAE, you get the data, for example, amnesty images, and you try to map each image in the latent space of normal Gaussian, right? By doing that, 0 goes to this part, and 1 goes to this area, and 3 goes to this area, and so on. So the idea is that latent space, you do some kind of clustering by mapping a similar point to the similar areas in latent space, right? So it's very similar to in unsupervised skill discovery. So you want to map a sequence of action to some distinctive region of latent space. So actually, unsupervised skill discovery is a very big area of recent RL research. So why we need to learn skills from environment? The first one is we can accelerate training on downstream tasks. So given the environment, you can define many different tasks. However, you first discover skills, and once you learn the skills, then you can, no matter how you define task by reward function, you can fast adapt to new task. So this is related to transfer learning too. And the second thing is that we can, so suppose that you want to control a helicopter, and you want to control helicopter using RL, and you know the physics of a helicopter, right? But important thing is that you have to define a good reward function to correctly control helicopter. So in practice, it's very tricky to define how we can define reward to control a helicopter. So, however, if you first discover skill discovery, then you can easily define which is good reward or not. So yeah, actually, if you have no previous knowledge about unsupervised skill discovery, then you need to think of VAE. So our goal is we need to learn skill policy with a good mapping from Z to skill. So prior methods can be classified into two different areas. So the first one is latent first method, and the second one is trajectory first method. So from this part, the context is a little bit difficult if you have no previous background knowledge, but I will try to explain the core things. So in latent first method, you first sample Z, and this is Z is sampled from fixed prior P of Z, and then given this Z, skill policy control your agent. So it means that it generates a trajectory. So trajectory can be defined on sequence of stage, and then you reconstruct Z from delta. By doing that, you can get good embedding of Z. So these four methods are representative one in latent first method. So you can think of VAE. So VAE, you have a data and you have an encoder, and encoder embed Z X to Z, and you take decoder, and decoder has an input of Z, and try to reconstruct S prime, and X prime should be similar to X. So here you can define reconstruction loss, right? By doing that, you can make encoder and decoder correctly reconstruct X from this to encoding and decoding process. And in VAE, there's another constraint. The constraint is that Z should follow normal Gaussian, right? So how we can define the distance between distribution? So in many cases, we use KL divergence. So basically, divergence is a weak concept of distance. So yeah, encoder distribution of data, and Z should be small as possible. So this is also minimized. So that's the basic idea of VAE. So in this particular example, you can think of this is a data and this is a latent space Z. However, here we first sample Z. This is a little bit similar to GAN. So in the GAN, you first sample Z and then try to reconstruct data. And in GAN, they use a classifier to measure the distance between two distributions. I mean, data distribution and fake data distribution. So anyway, so this is a little bit similar to GAN. And the second approach is trajectory first method. So here you have two different policies. So the first policy is you first sample delta with another policy. Here, another policy means sampling policy. And then you also need to control the agent too. So given this delta, trajectory tau, you encode tau to Z. And there's another policy called the skill policy, and skill policy try to reconstruct tau, and then we try to make the reconstruction loss is minimized. So there are two popular approaches in this category. So this is a known fact in previous research. Latent first method learn less interpretable skills. So it means that trajectory first methods is useful to interpretable skills. And yeah, the second bullet means that trajectory first methods increase interpretability, but they only maximize the diversity of the trajectory, not considering discriminability. So probably diversity and discriminability sound similar, but they are different. So let me give one example first. So this is a experimental result. So as you can see, the color codes different skills. But the idea is that diversity means that how your policies cover state space, right? Di and L also diverse. However, it's not discriminative because, as you can see, there are many overlaps between different colors. So it means that this is pretty diverse. However, it's not discriminable. So the idea is that our approach is not only diverse, very diverse, and at the same time, our approach is discriminable. Okay, so second approach is that the third point is that if your environment is too complex, then learning skills, learning diverse skills and control your agent are too difficult. So, okay, so let me give one key ideas of eyeball method. So here we have two ideas. The first one is that we use some kind of hierarchical RL. Hierarchical RL means that in this particular example, sampling policy have two roles. The first role is to control your agent, and the second one is generate diverse trajectory. So doing two different things is too burdensome for this policy. Therefore, we split the task. So the idea is that we have a high-level policy and low-level policy. High-level policy just to generate goals, which are diverse, and actual control is done by linearizer. So the idea is that low-level policy takes stage and goal, and it generates actual action for the agent. And then sampling policy only care about diverse goal. So you can think of this this an example of a hierarchical RL. And the second approach is that, as you can see the name of our approach, we apply information bottleneck approach. So as I said, you can think of this formulation as VAE, but later beta VAE is proposed. So beta VAE use information bottleneck objective, and the main difference between them is that beta VAE is more disentangled, can learn more disentangled representation. So this entangled representation. So the idea is that previous approach, the objective of previous research is like VAE. However, we apply information bottleneck framework. So you can think of our approaches like beta VAE. By doing that, we can get better disentangled representation. By doing that, our latent representation is more discriminative. So that's the basic idea. So yeah, so there are two key ideas, but understanding these two ideas is too tricky. So I just mentioned high-level ideas only. So in our experiments, we perform many different experiments. So for example, these are the learned skills. So in ant environment, exploration is main goal. Therefore, each color represent different skills. So given ant, we have no external rewards, but they just discover this eight good sequence of actions as skills. So once you have these skills, then you can solve some simple task like goal reaching, zero shot learning. So it means that you don't need any learning process. So you can just run unsupervised learning, and your agent is enough to learn to achieve reaching goal tasks. So this is another learned skills for in humanoid environment. So there are 4 different tasks, and there are also 4 different tasks in half cheetah and hopper environment. So this shows the visualize the learned skill. So as you can see, our approach is the most most diverse and most discriminable. Yeah, we can show other techniques, and this is the performance of downstream tasks. So as you can see, we our approach can quickly achieve the highest average returns with very small epoch, because our learned skills are very useful than those discovered by other methods. So so this is the goal of this is the conclusion of the second paper. So we propose eyeball, and this is the approach to unsupervised skill discovery. And so our approach can discover more disentangled and interpretable skills because we apply information bottleneck approach, And linearization of environment means that skill discovery, I mean, the control policy of skill discovery has too much burdens to control the agent, not only control the agent, but also generate diverse trajectories. But by applying the concept of hierarchical RL, we split these two tasks into two different policies. As a result, our approach outperforms other skill discovery methods on both the information theoretic evaluation and downstream tasks. Okay, you can also find the codes, and if you have any questions, you can contact first and the second authors. So actually, I have no time to discuss the third paper, so this is a joint work with Professor Hong-Lang Lee at Michigan University. So this is also unsupervised skill discovery techniques, and the main goal is we want to, so yeah, this is some tricky things, but in many cases, in most of unsupervised skill discovery approach has an objective to maximize the mutual information between latent space Z and S. However, mutual information is scale invariant. So it means that no matter how you compute how you multiply a constant number A, the mutual information is the same. As a result, previous method has some only learn static skills. In order to encourage dynamic skills, you have to add some heuristics. Otherwise, they would learn static skills. However, we propose a new objective and new constraint, Lipschitz constraint. So by doing that, we can encourage more dynamic skill discovery. So that's the main contribution of this work. So I don't have time to discuss this paper, but yeah, you can also download the code, and if you have any question about this work, then please ask me after the lecture. Yeah, thank you for your attention, and I would like stop my talk here. Yeah, thank you.